Hey guys, in this video I will be deriving the initial and boundary conditions in dimensionless form for the dimensionless PDE of diffusivity. Gosh, my writing is atrocious. Diffusivity of in radial flow for a slightly compressible fluid. Okay, that's a real mouthful. Okay, so from the previous video, you can recall that the dimensionless diffusivity equation is 1 over r sub d dou over dou r sub d dou p sub d over dou r d is equal to dou p sub d over dou t sub d. Okay, so again, any PDE is not able to provide us with solutions if we do not have some kind of conditions. So on the left hand side we have a second order PDE with respect to I already wrote the 2 there, with respect to r, which is a location, and here we have a first order PDE with respect to time, which means that we'll need 2 conditions to solve for the location domain and 1 condition to solve for the time domain. Okay, so now let's look at the conditions. We'll look at, what color did I use for time last time? Okay, so we'll look first at the initial condition, and this is to solve for the time domain. Oh gosh. Okay, so the assumption is that at time t equals 0, p equals p sub I. So the reservoir, this means that the reservoir has a constant uniform pressure at t equals 0. Okay, and we can express this condition typically as follows: p of r t equals 0 equals to pi. So now the question is, how can we convert this to dimensionless form? So let's recall the definition of dimensionless pressure. P sub d equals kh pi minus p over 141.2 bq mu. Alright, so p sub d at p equals to pi is going to be equal to kh times pi minus pi over 141.2 bq mu, which is just equal to 0. So we can actually rewrite the equation simply, the condition simply as p sub d r sub d t sub d equals 0 as 0. So how did we get to this point? Namely, how do I know that this can be the r can replace the rd and that t sub d is equal to 0? Alright, so let's go to that. Well, recall that r sub d is equal to r over rw. So r sub d is scales linearly with r, so we can directly replace r with rd. And honestly, that should be enough to explain why. Okay, and how do we know that t sub d is equal to 0? So let's recall the definition of dimensionless time. That definition is constant is 0.0002637 kt over phi mu c sub t r sub w squared, and when t sub d when t is equal to 0 is simply 0. So this condition is justified. Alright. So this is the initial condition.